Hey everybody, Mr. Piercy here, and what we're going to be looking at in this lesson is how similar figures change with the scale factor when we compare the area and perimeter. How does the perimeter of similar figures and the area of similar figures react when we have a scale factor applied to them? So here is just a very quick example demonstration about how this is going to work. So I have on the left side here three triangles where from the first triangle to the second triangle I doubled the dimensions, and from the first triangle to the third triangle I tripled the dimensions. So when I take a look at those values, let me pick a different color here instead of just red. If I look at the ratio of the perimeters from figure 2 to figure 1, that's going to give me 12 to 6, which is, oops, not 1/2, but 2 to 1, which is what most people intuit was going to happen. If I double the dimensions, the perimeter should double because the perimeter is made up of the side lengths. Well, if we compare the areas, and let's pick another color here. Let's look at the same thing, but for the areas. Let's look at the areas of these things. So if I compare the area of figure 2 to the area of figure 1, here the area of the second figure is 8, and the area of the first figure is 2. Oh, I'm not paying attention here. Which would simplify to be 4 to 1, or 4. So here, where I'm saying the scale factor is 2, between figure 2 and figure 1, it doubled. The scale factor is 2. The area did not double the way perimeter did. The area quadrupled. It went by a factor of 4. Well, let's see what happens when I compare figure 3 to figure 1's perimeters. So if I'm looking at the perimeter of this and the perimeter of this, that's going to give me 18 over 6, which would be 3 to 1, or just 3. So from the first one to the third one, the dimensions tripled, and the perimeter, the ratio also tripled. Well, let's look again at the areas. So the areas here of figure 3 and figure 2, I'm sorry, figure 3 and figure 1. Here we're going to get, and I'm going to have to move that. So let me just kind of scroll down a little bit. So let me try it again. 3 to 1 for the areas. Here I had an area of 18 versus the original area of 2, and that gives me a ratio of 9 to 1, or 9. And what I'm trying to illustrate here is what the stuff in the box is telling us for the area of similar polygons theorem. The ratio of the sides change proportionally by whatever the scale factor is. So if the side lengths double, the perimeter doubles. If the side lengths are cut in half, the perimeter is cut in half. But area doesn't change at the same rate because area is not a linear measurement. Perimeter is made up of linear pieces, segments. So it makes sense that if I affect a change on a linear measurement, every linear measurement should change at the same rate. I should say. Whereas area, because area is not a linear measurement, area is a value that is squared, area doesn't change at the same rate. It changes by what the scale factor is squared. So down here, what I have is, please make sure you include this in your notes. Perimeter does change by the scale factor, however area changes by the square of the scale factor. These two statements can be summarized with the equations that I have here. The perimeter of the new one is equal to the perimeter of the old one times the scale factor. And here the area of the new one is equal to the area of the old one times the scale factor squared. If you kind of keep those two things in mind, a lot of the calculations that you wind up doing when you're looking for perimeter or area of similar figures can be relatively easy. So let's take a look at how we're going to just compare the ratio of these things. Here we're told that these two triangles are similar to each other, and we want to find the ratio of the shaded figure to the unshaded figure. So if I'm looking at the shaded to unshaded, whatever is written first gets put in the numerator. So because it says shaded to unshaded, we have to write our ratios this way, from the numbers of the shaded triangle to the unshaded triangle. So when I work these out, I'm going to just look at the corresponding side lengths. So DF and AC compared to each other, or those are corresponding side lengths, so we're going to say 9 over 6. Well, we always simplify our fractions, so that would just be 3 over 2 or 3 to 2 as a ratio where we just use a colon. So theorem 6.1, that's the theorem that says that perimeter of similar polygons are proportional to each other. And the 11.7, that's the one that we just saw on the previous screen that says that areas of similar polygons changed by the scale factor squared. Well, here the perimeters would just be 3 to 2, the ratio of the perimeters. But the ratio of the areas, as I just explained, does not change at the same rate. It changes by the scale factor squared. So we would say 3 squared to 2 squared, which would be 9 to 4. So the ratio of the areas, remember, changes by whatever the scale factor is squared. So 3 over 2 squared simplifies to be 9 over 4. Now here is a kind of question that I've always kind of wondered how people work it out, but I think about it more in terms of t-shirts, and I'll kind of explain what I mean by that here at the end of the problem. So we have two rectangular pieces of aluminum window screening. One is 15 feet long and costs $135. The other one is similar and is 20 feet long, and it is sold by the square foot. So what is the cost of the larger piece? Well, if we look at the information that was given to us, the ratio of the lengths that we are given from the longer one to the shorter one would be written as a ratio of 20 to 15, but when I simplify that, I get 4/3. So the ratio of the areas changes by that squared, so that would be 4 squared and 3 squared, so the area ratio would be 16 to 9. Well, we can use that ratio and create a proportion that we can set up and solve to find the cost of the equivalent larger figure. So the ratio of the area is 16 to 9 is equal to the cost of the larger figure over the cost of the smaller figure. And when I cross multiply and solve for x, I get $240. Now, this kind of makes sense. Something that's bigger should cost more. And it's based off of how much the scale factor is. You're finding the cost of a screen. It's a two-dimensional object. So if it gets bigger, it changes by the scale factor squared, which is exactly what we're seeing. But I always thought about this in terms of t-shirts. You know, if you go to the Target or Walmart or whatever, and you're looking in the t-shirts, all the t-shirts from small to 2X, they might be all of them $10. But you know that they clearly use much more material for the 2X size t-shirts than they did for the small size t-shirts. So why doesn't the cost change proportionally by the area the way that we're looking at in this example? So there has to be some other stuff going on as far as how the manufacturers are transferring the cost onto the consumer to make the size of a small garment and the size of a 2X sized garment the same price. But I always wondered about that. How do they figure that cost? So anyway, at this point, go ahead and pause the video and answer these two questions based on what we've seen in the two previous examples. And when you're done, go ahead and hit play and see how your answers look compared to mine. All right, so hopefully we have some good answers here. So we want to find, they're telling us again that the two triangles ABC and DEF are similar to each other. And we want, again, the ratio of the shaded to unshaded perimeters and areas. So I'm going to take the dimensions from triangle ABC and I will place them over the dimensions for triangle DEF because that's how it's asked to do, shaded to unshaded. So in this case, I'm going smaller on top, larger on bottom. So we set it off for perimeters. We would say the ratio would be 12 over 15, which would simplify to be 4 to 5. Well, the ratio for the areas is whatever the perimeter ratio is squared. So that gives me a ratio of 16 to 25. Now in example 2, we're going back to, or for problem 2 here, we're going back to the last example where we're talking about the aluminum screen. Well, now instead what it's doing, it says the longer roll is going to cost $200. What would be the cost of a shorter roll of similar dimensions? Well, based on the information that we have, there we go, the ratio of the areas was 16 to 9. Well, in this case, the cost of the larger roll is given to us to be $200. So I say the cost of the smaller one is in the denominator X, and then just cross multiply, and the cost of the smaller one would be $112.50. Now moving on, again, this is very similar to the one that we just talked about with the aluminum screens. Here we have billboards. Large billboard is 12 feet by 27 feet, and a smaller similar billboard has an area of 144 square feet. Well, let's find the height of the smaller billboard. Now here it's giving us a drawing to work with, and I always think drawings are very helpful whenever I am given a problem that uses figures but they don't actually provide me something to look at. I'll always just sketch something out to see what am I working with. Well, based on what we have a big rectangle that has a 27 by 12, and so I can find its area to be 324. And the area of the smaller rectangle was given to me to be 144. So that's all the information that was given to me. Well, because they're giving me the ratio, or because they're giving me the areas of the two figures, essentially, I can find the ratio of those two areas and say here, if I take the ratio of the areas, I can then find the ratio of the sides as well. Well, if I say the ratio of the large rectangles area, or small rectangle area to the large rectangle area, that simplifies to be 4 to 9. Well, if I had to square the perimeter ratio to get the area ratio to go the other way, we're going to take the square root of those. So we're going to take the square root of the 4 to 9 ratio, and that gives me a ratio of 2 to 3 for the dimensions of the smaller rectangle, the smaller billboard. So anything that's going to be on the smaller billboard is going to be 2/3 the length of the larger billboard. So that allows me to work out that the missing height of the smaller billboard should be 8 feet. I don't know if that's a really big billboard or not. 8 feet. It doesn't sound like it's very big. Probably not something you want to have on the side of the highway anyway. But here, go ahead and again, pause the video and work out this problem on your own. And when you're done, hit play and check to see how your answers look compared to mine. All right, guys. So hopefully we have a good answer here. It's going back to the billboard problem. Suppose the area of the smaller billboard is 225 feet instead of the 144 feet that was given to us. And again, it's just kind of recycling the same question. Find the height of the smaller billboard. Well, because the area of the smaller one changed, the ratio is going to change also. So the ratio of the areas, when I say 225 to 324, the smaller one to the bigger one, that works out to be 25 over 36. So when I take the square root of those numbers to get the ratio for the sides, that works out to be 5/6. So that means everything on the smaller one, the sides, will be 5/6 to be the dimensions of the larger one. So again, setting up the proportion here, I would get a height on the smaller billboard to be 10 feet. Now this next example here is probably my favorite and my worst problem on this set of notes because I really like what they're doing. I just am not really a big fan of how they're doing it. So I'm going to walk through how they did it first, and then I would kind of show you how I would do this. If I was just given this problem without any kind of setup with how they're walking us through the steps, how would I do it? Okay, so we have a stop sign that's in the shape of a regular octagon. Each side of one is going to be 2 feet, and the area of that is about 19.3 square feet. Where you're going to make a mat, and if it's a perimeter of 72 inches, find the area of the mat to the nearest square inch. Now, again, the first thing I want to do is I want to know what am I looking at. So we have an area of one octagon to be about 19 square feet and a perimeter, and it tells you that each side is 2 feet, so that would be about 24 inches. Because if you notice right away, they're giving us some dimensions in feet and some dimensions in inches. So I want to know which one am I going to be working with. Well, it tells me that the other octagon has a perimeter of 72. If I divide that by 8, that means that each side has to be 9 inches or about 3/4 of a foot. Okay, so there's the, they're not giving me anything to look at here, so that's what I'm going to give myself to as a diagram to refer to if I need it. So we have similar figures, so that means that the ratios of the areas and the ratios of the sides follow that same pattern, as that the sides are just going to be like whatever the ratio works out to be for the scale factor, but the area will be whatever that value is squared. Okay, so moving on, here's step one, find the ratio of the lengths of the rug and the mat. So we know the perimeter of the rug is given to us to be, or we know the side length is going to be 2 feet and the perimeter of the mat is 72 inches. Well, because right away we have a dimension mismatch, they're saying and one is in feet and one is in inches, we have to convert from one dimension to another. Okay, so in this case, the way they're having us work it out is we're going to put everything in feet. So the perimeter of one is going to be 16 feet, and when I convert 72 inches into feet, that's 6 feet. And if you need to see how I did that, that's on the left. So the ratio of the corresponding sides, and therefore the perimeters, would be 8:3. So now we can use that ratio to find the areas. So because we can take those values and we can square them to find the ratio for the areas, here we can say 8 squared over 3 squared is equivalent to 19.3 feet over the area of the smaller mat that we're looking for. So cross multiplying and dividing. So cross multiplying, really what I'm going to do is I'm going to multiply 3 squared to the 19.3, and that'll give me 64 to be equal to 173.7. And when I divide by 64, that gives me an area of about 2.7 square feet for the mat. Now the problem is that ultimately they're asking us what's the area in square inches. So that means I have another conversion that I have to do. So 1 square foot is equivalent to 144 square inches. So if I multiply the 2.714 by 144, that gives me about 391 inches squared. So that's how they're kind of working it out. Now let me go ahead and walk you through my mind what I do when I see a problem like this. So when I see a problem like this, I'm going to just kind of identify, well, what information is given to me and how am I gonna, what do I need to find? So we know that we have sides in 2 feet, an area of about 19.3 square feet, and we make a mat with a perimeter of 72 inches, and we want to know, this is find the area of the mat to the nearest square inch. Okay, So if I'm looking for my final answer to be in square inches, you can kind of do what the problem did and you can convert at the end, or you can convert everything into inches at the beginning and go from there. Personally, I always like to know what dimension does my answer need to be in, and I'm going to do all my conversions first because I know from experience that if there's unit conversions that have to be done, if you wait until the end, chances are if you're going to forget something, it's going to be that conversion at the end. So I always try to convert at the very beginning. So the way that we're looking at this is, again, I can say the way that the ratios work out, since they're giving me 19.3 square feet, I can say 1 square foot is equivalent to 144 square inches. So I'm going to take the 19.3 square feet over x square inches, and I'm going to just find out, well, how many square inches is the one that we start off with, because my answer is supposed to be in square inches, so what is it going to start me off in square inches? So if I say 19.3 times 144, that gives me about 2,779.2 inches squared. Okay, so here, this is 19.3 square feet, or 2,779.2 inches squared. Well, now I want to know what is the area of the new one. Well, here, this is where I'm going to refer back to kind of those simplified equations that I had at the very beginning. The area of my new shape is equal to the area of, oops, put that backwards. The area of my old shape multiplied by the scale factor squared. Now, real quick about the scale factor, we know that the scale factor here is 8/3, but this one here would be on enlargement because the ratio 8:3 is larger than 1. So that scale factor is going to take something and blow it up. Well, we're starting with something big and we're going to something small. So I'm actually going to take that and turn it upside down. So I'm going to say the area of the new one is equal to the area of the old one, which is the 2779.2, and I'm going to multiply that by 3/8 squared. So if I multiply that by 3/8 squared, we're still going to get the area of my new one to be 390.825 inches squared. And I think, I don't know, I know it all ends up to be the same in the end, but this is really what my mind goes through when I have a problem that I have to work out, where I'm changing areas like this. But either method works to be the same answer, so whichever method you prefer is fine by me. I can follow your work and see what you're doing, but that's what my mind, how it works through it. But so go ahead and try working it out again. Work out problem number 4 on your own and see what you come up with. And when you're done, hit play, come back and see what my answer looks compared to yours, and we'll go from there. All right, so I'm hoping and trusting that everybody's doing what I'm asking you to do and that you're actually pausing the video and working this out. So here we have two rectangles that are similar to each other. The perimeter of one rectangle is 48 inches. Rectangle 2 gives me the length and width, and it's asking me what is the area of rectangle 1. Now it's not asking me for anything specific as far as feet or inches, so since they're giving me dimensions and inches, it's understood that the area should also be in inches. Now, again, they're not giving me, somewhere, there we go, they're not giving me anything to work with. So the first thing I want to know is I'm going to give myself a diagram. So I just draw two quick rectangles, and I know what is all the information that they gave me. We know the perimeter of one, and they give me the dimensions of the other one. So with the dimensions of the other one, I can find out that's perimeter is 96 inches or its area is 540 inches squared. So we want to know what the area is. So if I look at the ratio of the perimeters, because I'm not going to try and figure out the side lengths of the smaller rectangle if I can get the same ratio with the perimeters. The perimeter of the figures from rectangle 1 to rectangle 2, and I'm writing it that way because we want to know what is the area of rectangle 1, so I say 1 to 2. 48 over 96 simplifies to be 1/2, so the scale factor between the two triangles going from the big one to the small one would give me a ratio of 1/2. It's a reduction. So the equation that I have is the area of the new one is equal to the area of the old one times the scale factor squared. So I take the area of the bigger rectangle, 540, multiply it by the scale factor, 1/2 squared, and my new area is 135 inches squared. And that's going to pretty much wrap it up for this lesson. And the key things that we need to understand is that similar figures, area changes differently than perimeter. Perimeter changes by the scale factor, whatever that is. Area changes by the scale factor squared. If we're enlarging something, the ratio of our scale factors has to be bigger than 1. If we're reducing something, the ratio of our scale factors has to be smaller than 1 but bigger than 0. And that's going to wrap it up for this lesson. If you have any questions, you know how to get in touch with me. Send me a comment, leave me a comment, send me an email, come see me in class, whatever you need to do. But until next time, ladies and gentlemen, thanks for watching and take care.